All right. Welcome to this week's Non-Computative Geometry and Topology seminar. It's our pleasure today to have Peter Zeman from the Technical University of Denmark, who will tell us about quantum automorphism groups of graphs.
Thank you for inviting me. In this talk, I will talk about, as you said, quantum automorphism groups of graphs. And this work is based on those two quite recent papers with those people that are listed here. And so I'm currently a postdoc with David Robertson, and the project we are working on is in the intersection of graph theory and quantum information theory. So somehow graph theory is used to study some concepts in quantum information theory. In particular, the area of graph theory is graph homomorphisms, which I will talk about a little bit. And this, and at some point in some works, quantum groups of graphs occur, and these two works are sort of like bridge between those two areas, in some sense, since probably from the quantum group side, this like there are two groups of people that work on quantum groups and that work on graph theory, and those groups usually don't know much about the things that the other ones work on. And basically, what I would like to a lot focus on in this talk is to show you some techniques from combinatorics that we used to obtain some like in combinatorics, the combinatorial analog would be some simple results about automorphism groups of graphs, but for some reason, these results did not at all exist in the relatively recent, but not that recent field of quantum automorphism groups of graphs. So let's start with just the notion of the graph isomorphism. So two graphs are isomorphic, basically, if we can find a permutation or a bijective mapping between the vertices of one graph to the other graph, such that this mapping preserves adjacencies and non-adjacencies. So in other words, the graphs are exactly the same up to some relabeling of the vertices. We denote it like this. And so alternatively, this alternative two points of view will play a role here. So alternatively, one could view it if you take the adjacency matrices of the corresponding graphs, and you would have a permutation matrix that has to commute with those adjacency matrices. So that's an equivalent definition of isomorphism of graphs. And another very impressive theorem was given by Lovász in the previous century, in 1967, which basically characterizes this relation of being isomorphic by the following counting of homomorphism. So homomorphism of between two graphs is like isomorphism, but you relax the condition a little bit. It's a mapping that only has to preserve adjacencies. So, for example, you can have a homomorphism from a bipartite graph to an edge. And this notation means that we count the number of possible homomorphisms from some graph F to the graph G. So the isomorphism relation between two graphs is characterized by homomorphism counting. So the homomorphism counts the number of homomorphism from each possible graphs to those two graphs. If it's the same, then the graphs are isomorphic, and also the other way. Now, it's not necessary to just restrict ourselves to all graphs. We can use various families of graphs. So there is a similar notion of homomorphism indistinguishability, where we take some family of graphs and do these homomorphism counts within that family of graphs. And then we get a notion of homomorphism this indistinguishability, which depends on that particular class of graphs. So here we have a table of some results And this is the Lovaas theorem, where we take the family of graphs to be all graphs. When you take various other, let's say, natural families of graphs, you get other similarity relation between those classes of graphs. Like for cycles, if you just take cycles, then this corresponds to the cospectrality of adjacency matrices, which means that the multisets of eigenvalues of the adjacency matrices of graphs is the same. Cycles and paths would be cospectral complements. Trees, this is actually fractional isomorphism. Fractional isomorphism you get by relaxing this equation here. So instead of a permutation matrix, you would use something called doubly stochastic matrix, which is basically that the rows have to sum to 1. And then there is a class of bounded tree-widths, tree-width at most k, and this corresponds to indistinguishability by something called k-dimensional Weisfer-Lehmann algorithm, which I will talk about later. But it's just some procedure on graphs, but I will talk about it. But tree-width k is some parameter of graphs which tells you how much the graph is close to a tree. Okay, and then tree depth is something similar. So for various classes, we have notions, and then this is the important one here, that if you take planar graphs, this is a quite recent result, that this actually corresponds to a notion of quantum isomorphism. So homomorphism indistinguishability when you restrict yourself to planar graphs. So in other words, what we will see, being quantum isomorphic, the result is that it's like having the same homomorphism counts from planar graphs. So, okay, so just a little bit about what is this quantum isomorphism. So this
small home, this is just numbers.
Numbers, yes. Numbers. Yeah. Number of homomorphism, yes. So this notion of quantum isomorphism comes from the notion of a non-local game, which is an important concept in quantum information theory. I will just briefly introduce it. So in the game, you have 2 players, Alice and Bob, and a verifier. And both of the players have some finite input sets, xa, xb, corresponding to those players, and some finite output sets, ya, yb. And then you have a Boolean predicate, which is basically a function, 0, 1 function from this Cartesian product. And so basically the players are asked a question from the input, and they have to answer. And the players win if this is evaluated to 1. They cannot communicate after receiving questions, but they can decide on a strategy, what they will do. And there is only 1 round of the game, and one is concerned with perfect strategies in which players win the probability 1. And now, what kind of strategies can you have? You can have deterministic strategies where you have just some functions which deterministically say what will be the answers for Alice and Bob. Then you can have randomized strategies which are not that much better, but where you can use some randomness potentially. And then you can have quantum strategies where these Alice and Bob will share some entangled quantum state and use it to get answers. So let's immediately look at this GH isomorphism game. So we have 2 graphs, G and H. And the intuition is that Alice and Bob want to convince the referee that the graphs are isomorphic. So here is the setup, basically similar, that the Alice and Bob are asked some questions. Well, now the questions are, the input sets are the vertices of the graph, also the output set. And what must be satisfied is that the relation between H and H prime is the same as a relation between G and G prime. So relation in the sense adjacency, non-adjacency. So again, the players cannot communicate. There is only one round, and they must win with a probability 1. And the theorem is that basically these classical players can win, classical in the sense that they have like a deterministic strategy, if and only if the graphs are isomorphic. And now to define the quantum isomorphism is to basically turn this definition around and say that the graphs are quantum isomorphic if quantum players can win this game. So that's basically a definition that the graphs are quantum isomorphic if quantum players can win this GH isomorphism game. And what does it mean? Just briefly, is that here we have a shared entangled state between those players. And basically, so Alice and Bob share this quantum system in some state psi, which is basically a unit vector in some Hilbert space. And upon receiving this vertex G, Alice performs some measurement, EG, and this EG is basically some set of operators satisfying these conditions, which is based on the quantum formalism. And the same is done by Bob, that he does the same. These operators can commute, and there is some probability that the players respond H prime given G prime. So one can reformulate this in using the notion of quantum permutation matrix. So here we have this, that a matrix whose entries are Pij, and these are elements of some sister algebra, is a quantum permutation matrix, also called magic unitary, if we have this, that each Pij is a projection, so it must satisfy these relations, and these matrices in sort of in the row and column must sum up to 1. And the theorem by Lupini, Manchivskaya, and Robertson is that this quantum graph isomorphism is equivalent with commuting with a quantum permutation matrix. So it can be expressed in a similar framework as the other similarity notions, like isomorphism is just commuting, or fractional isomorphism with doubly stochastic matrix. And here we have commuting with this quantum permutation matrix. So formally, this is just written out. What does it mean formally that these things commute? Yes, and it's important to say that quantum isomorphism is actually an undecidable problem compared to the graph isomorphism problem, which is clearly decidable, where you just can try all bijections between two graphs. And there, I'm not showing it here, but there is an example of graphs that are not isomorphic, but are quantum isomorphic. Right, now I want to get to the quantum automorphism groups of graphs. And let's just recall that the automorphism groups of graphs basically express the symmetries of graphs. And so basically an automorphism is just an isomorphism from a graph to itself. So it's a bijective mapping which again preserves adjacencies, and similarly automorphisms form a group under composition, and it can be equivalently expressed using such equation that the adjacency matrix has to commute with a permutation matrix. Yeah, so this in particular graph has a dihedral group D5 as an automorphism group. We can do just reflections and rotations here. Okay, so you probably know much more about these things, but I'm just mentioning here that we have the notion of compact groups. There is a correspondence between compact groups and commutative sister algebras. Then when we take the sister algebras to be non-commutative, then from there we go to compact quantum groups. So we now immediately say what is a quantum automorphism group of a graph. So this is definition according to Banica, and basically, so we say what is this sister algebra in this case. So the C of QG, that's how we'll denote the quantum automorphism group of graph, is the universal sister algebra generated by the elements Pij and satisfying basically these following relations, which we had similar relations before. And these first two relations correspond to the fact that sort of the P made up of these entries Pij is a quantum permutation matrix. And this last one corresponds sort of to this commuting equation. So if we require those Pij to commute, then we get that the C of AUG, the algebra of functions on the automorphism group of graph, and the Pij would be a function taking an automorphism to the Ij entry of the matrix representation. And this matrix P is then called a fundamental representation of QG. Now let's connect it to quantum isomorphisms, and so let P be the fundamental representation of QG, and we can define the following relation that Ij corresponding to some vertices, let's say, of the graph, I is in relation with J if Pij is not 0. Now, the theorem or lemma is that this is actually an equivalence relation, and the orbits of or quantum orbits are defined to be these equivalence classes of this relation. And so how we connect it with the isomorphism, quantum isomorphism, is that if G and H are connected graphs, then they are quantum isomorphic if and only if there exists G, one vertex in the first graph and one vertex in the second graph, which are in the same orbit of the union of the graphs, which is sort of mimicking what is expected in classical automorphism groups of graphs. I will mention it also later. And this is a very important theorem, which will actually provide us with the combinatorial tools that can be used to study quantum automorphism groups of graphs. And this is exactly the following. So let G be a graph, and now I will define this two-dimensional Weisfeld-Lehmann algorithm shortly. But it's some kind of algorithm that creates a partition on the graph, which is automorphism invariant in the classical automorphism group. So we have this partition of the vertices, and which is constructed, let's say, by this two-dimensional Weisfeld-Lehmann algorithm. And if two vertices belong in two different colors or partitions, then this Pij is equal to 0. So in other words, they are in different quantum orbits. So this is very important, very, very useful tool in general. And it's actually, this result is due to also these people. And this is very powerful tool, powerful combinatorial tool to use. And it appears in many, many different areas. So it's actually, I think, quite fascinating result. And there is also, and I will talk about this, there is also a better version of this two-dimensional Weisfeld-Lehmann algorithm, but it's no longer useful for quantum groups because, as far as I understand, it's not really possible to define quantum orbitals like analogs of orbitals, which are basically the orbits of the action of the group induced on the Cartesian product of the set on which is acting. So Yeah, so if you remember in the beginning, we had this slide where this notion of k-dimensional Weisfer-Lehmann indistinguishability is equivalent to homomorphism counts into graphs of this bounded tree-width. So then there was the result by Robertson and Manjiska, which says that quantum isomorphism is equivalent to counting homomorphisms from planar graphs. So this is another reason why higher dimensional Weisser-Lehmann doesn't work here. Is this because all planar, like all tree-width graphs at most 2 are planar, but tree-width graphs at most 3 are not all planar. So that's another, let's say, reason why this Weisser-Lehmann doesn't work anymore in higher dimension. Now let's finally talk about this. Okay, Weisser-Lehmann in a bit. So now I want to a little bit talk about the graph isomorphism problem, because that's actually the motivation for this Weisser-Lehmann algorithm. So the graph isomorphism problem is just a computational variant of this graph isomorphism. So basically we get 2 graphs and we want to answer yes if and only if the graphs are isomorphic. And there is actually a polynomial time equivalent problem, which is computing the generating set of the automorphism group of the graph. So actually this is very similar to what we said before about quantum groups and quantum isomorphism, that to see this, why this is equivalent, or at least one direction, is to just consider 2 connected graphs and then take the disjoint union, and basically if there is an automorphism taking one to the other, then we know that they must be isomorphic when there is a generator in the generating set of the automorphism group. So the currently best known algorithm for graph isomorphism runs in this time, which is called quasi-polynomial, and it is actually heavily based on group theory. And just why this problem is actually interesting is that from the complexity theory point of view, actually you can have basically 3 things that can happen, and each of them would be very interesting. Like if so the goal is usually to solve some problem in polynomial time. And if you could solve it in polynomial time, then it means that you probably have to invent some new mathematics. If it was NP complete, which is like the notion of algorithmic hardness, then something called polynomial time hierarchy collapses, which is basically part of complexity theory. And if this collapses, then many people believe that this doesn't collapse. So they believe there is evidence so that it should not be NP complete. And when it's intermediate, somewhere in between, then it would resolve the famous P versus NP question. So this problem originated from some practical applications, but actually for practical applications, it's pretty much solved. Actually, by this Weisser-Lehmann that I will mention, it works very well in most of the practical cases. But yeah, so why is this problem actually difficult? Is that these algorithms are actually heavily based on group theory, and one of the main parts is to do some recursive algorithm, and the problem are different complicated actions of some large group. Like if we have this simple graph, then it has the automorphism group Sn, and it has the so-called natural action on the set 1 to 5, which is basically doing what you expect, just permute the vertices. But if you care to guess, okay, I'm missing an edge here. Oh no, what is the automorphism group of this graph, which is the well-known Petersen graph? Yeah, it's also S5. Sorry, S5. Yes, it was S5. No, yeah, it's S5, but now it's acting like on 10 points. And actually, you cannot find like a partition into non-trivial blocks. So like a partition that is preserved by the action, you can only partition it trivially. and this means that the action is primitive and you cannot do recursion. So the problem is in this isomorphism testing with large groups which have not quasi-polynomial order, but it is a large order and complicated action that you cannot decompose. Okay, so let's get to this Weisfer-Lehmann. So first, the simpler version of the Weisfer-Lehmann is just a color refinement algorithm, which is something that probably if you were given as a homework to solve the isomorphism problem, then probably this would be the first thing that would occur to you, is that you just take two graphs and you first color all the vertices uniformly. And now you look at each vertex and see what is the degree of that vertex. And if you know that the degree is different, then you surely cannot map it to some other vertex with a different degree. So then you can recolor the graph based on this. You see that the blue vertices have the same degrees and the red vertices have the same degrees. Now you iterate this process until you get something stable that no longer can be refined. And then basically, if you end up with a different colorings, then you can say that these things are definitely not isomorphic. But if you end up with somehow the same colorings, then you really do not know. Now, the Weisfer-Lehmann algorithm does something better. So instead of just coloring the vertices, it's coloring the pairs of vertices, right? So how does it work? So here we have just this very simple graph. And if we want to depict the pairs of vertices, we can just depict them by some arrows. So here is the pairs of vertices that occur in this graph. And we give it some initial coloring or initial partition. So this green color corresponds to the fact that there is no edge here. And this red color corresponds to the pairs of the form UU, let's say, and this blue corresponds to the edges. Now, we construct a new partition in the next step. Yes, in the initial coloring, and actually it will be like recolored, as you will see. So in the initial coloring, all pairs that correspond to the edges, to the actual edges, will be colored the same, and all pairs that correspond to the non-edges and the diagonal of the. Yeah.
We just decompose into graph and non-graph and trivial.
Yeah. And in the next iteration, we do the following counting. So for each pair UV of some color K, and every ij, we count the number of vertices such that there is such a triangle in the graph. So the base of the triangle is the UV with color K, and we count the number of vertices W such that there is a first step in color I and a second step in color J. Of course, this K, I, J can be possibly the same. They don't have to be all distinct. And then for each pair, we do this count. And then in the next step, we recolor the pairs based on these counts. So the next step here would look something like this. So actually you will get some new colors on here and a color and new colors here. And this actually makes sense because it should be approximating the orbits of the automorphism group. And this vertex got orange, these two vertices got orange color and this remained red actually makes sense because these two vertices here should be in a different orbit than this vertex. And of course, it doesn't work perfectly, but it works very well. And of course, you can construct some examples where it doesn't work But it's a very, as I said, the connection with the quantum groups is actually also approximates the quantum orbit. So basically, whatever is distinguished by the Weisser-Lehmann, you can also use it when studying the quantum group. Okay, so what we actually did, we colored the adjacency matrix. And now the idea of this Weisser-Lehmann, you can think of it as basically constructing invariants. In mathematics, we distinguish objects by constructing invariants, the dimension of a vector space or more complicated, like in algebraic topology, some homology groups. So this is something similar, basically, because we colored the adjacency matrix and we actually constructed some coherent algebra, which is generated by the following matrices. So to each color, you can actually assign a 0, 0, 1 matrix. So like this. So here you have these are basically 0, 1 matrices where the ones are exactly at those places which are of the same color. And so in this case, this coherent algebra would be generated by these 5 matrices. And it is like a matrix algebra satisfying the following conditions. So the first condition is that all of the matrices, so these generating matrices, might sum up to all ones matrix. So which is here clear that if you sum it all up, you get the all ones matrix. So then there has to be some subset of the matrices that sum up to identity. So in this case, it would be this orange matrix and this red matrix. They sum up to the identity. So this basically tells you that it's actually also approximating not only the 2 orbits of the graph, but also the orbits. So it should be more powerful than just the degree refinement. And then if you take any pair of matrices, if you use the bad student product, the component-wise product or Schur product, then you get the 0 matrix, and then you have the transpose matrix there. It's like, for example, here we have a pair of transpose matrices. And then the last condition is that the product of the matrix can be expressed in such a thing, in such a sum, and these numbers Cij actually are some constants that corresponds to this counting of triangles when it's finally stable. So we have this kind of matrix algebra on top of the graph, and if these algebras are isomorphic, then or non-isomorphic, then we can distinguish the graphs by this Weisser-Lehmann, and if they are the same, then we cannot make a conclusion. Now, you can go even.
So you're saying that if you are using the Weisser-Lehmann, then you are obtaining the smallest possible coherent.
Yes, yes. It's like basically it's the Weisser-Lehmann actually doesn't only have to be applied for graphs. You can start with any, because each of these matrices, 0, 1 matrices, can be also interpreted as just some binary relation, right? So you are basically starting with a bunch of relations, and the Weisser-Lehmann algorithm will find what is called a coherent closure. So the smallest coherent algebra satisfying these conditions that contains those relations. So, but when you want to apply it for graphs, you start with the specific 3 relations that I depicted, but it's not necessary to do that.
So it is on the graph, dot algebra generated by the adjacency matrix.
Yeah. Yes, in this case, it's just the adjacency matrix, but in general, you can start with any bunch of relations. Yeah, and you can go further. You can do k-dimensional Weisser-Lehmann. So here, instead of coloring two tuples, you will be coloring k-tuples. But I don't want to get too much into this because, as I said, it's not any more relevant for quantum groups. But there are some very interesting connections. Like, for example, the k-dimensional Weisser-Lehmann distinguishes 2 graphs if and only if these graphs are distinguishable by k+1 variable sentence with counting quantifiers. So, for example, here you have 2 graphs, that this cycle and these two triangles, so these are all regular graphs. So one-dimensional Weisser, which was the color refinement, is actually also called one-dimensional Weisser-Lehmann algorithm. This doesn't distinguish these two graphs because all of the vertices are the same degree, so it doesn't do anything basically. But you can distinguish them with two-dimensional Weisser-Lehmann. And this would correspond to some formula in 3 variables. You can implement this distance formula between these two vertices with 1 extra variable. So this would be like a 3-variable formula that also distinguishes those two graphs. So that's a connection to logic. And then there are many more very interesting connections like integer linear programming. As I said in the beginning, the homomorphism counting, that this homomorphism indistinguishability for bounded tree-width graphs is equivalent to being distinguishable by k-dimensional Weisser-Lehmann. Okay, let's go somehow back to the quantum groups. And so what we did in our work, we basically did a quantum automorphism group of graph version of 2 classical results, and I will mention them now. So first of all, like Fuchs theorem is quite old, and it says that for every graph there, for every group there, you can construct a graph with the isomorphic automorphism group. And actually, the quantum analog of this Fuchs theorem does not hold, even for quantum permutation groups. And so, but we are still interested in some quantum automorphism groups of restricted classes of graphs, because a lot of the results about quantum automorphism groups of graphs were in the spirit of analyzing whether a given graph has or does not have quantum symmetry, or maybe some calculations for some specific graphs, let's say. But it's kind of interesting that the quantum automorphism groups of trees, which we looked at, was not so much known. And so to do that, I want to recall a Breadth product of groups. So Breadth product of groups, and we will need the quantum analog of that. Breadth product of groups is like when we want to determine the automorphism group of 2 graphs. If they are non-isomorphic, we can just use the direct product to construct the automorphism group. But if they are isomorphic, it no longer works with the direct product, because if you look at the structure of the automorphism group, it's actually not a direct product. If it was a direct product, then this front square and the back square, this the Cayley graph, would be different. So, sorry, the same if it was a direct product. So it's just a nice depiction of the structure of the group. But this is described by the Breadth product. And by that, I just mean the following. So if I have 2 groups and a set omega on which Q is acting, then I can take the direct product, like for each element of the set omega, I take a copy of the group D, and take the direct product of this. And then the Breadth product is actually naturally defined as a semi-direct product, and the semi-direct product is defined by this action of Q on the coordinates of this let's say vectors or omega tuples in this direct product in a natural way. So just by action on the coordinates. So that's the Breadth product. And what we can do with this Breadth product is, for example, to determine the automorphism group of a disconnected graph by the following formula. So if we have like a bunch of copies of some graph, then this automorphism group will be just the automorphism group of the component rest producted with the symmetry group. And so in general, if we have a bunch of connected components xi, then we can use the following formula to compute the whole automorphism group based on the automorphism groups of the individual graphs. And this actually can already give us a proof of a very neat theorem. And this is one of the results that we will have a quantum analog for. This maybe is a very interesting theorem that could probably be even in some undergraduate course, which basically gives a description of all the automorphism groups of trees, and it's quite simple. So it's basically just an inductive description. So there is a trivial group in the class. And if there are two groups, then there is a direct product. And if there is a group, then it's rest product with a symmetry group. No, so how to see this? So if we have group G and H, then we can construct a tree with a direct product just by putting those trees onto a common root. And maybe if G and H is the same, so G equals H, we can just add one vertex to prevent swapping so that we have the direct product. And if you want to construct the rest product, it's also easy. We just take a copy of one tree or n copies of that tree, then attach it to the common root, and we get the rest product with the symmetric group. On the other hand, if you want to prove that these are all the groups, then we can just take any tree, delete the root. It's okay enough to consider rooted trees. Delete the root, apply the formula from the previous slides for disconnected graphs, and notice that only rest products and direct products occur there. So the group must be in this class. So now we have so the class Qt is the class of all quantum automorphism groups of trees that can be described as follows. So here, instead of the direct product, we will have a free product of the quantum groups. And instead of the rest product, we'll just have the so-called free rest product with a quantum symmetry group, Sn plus, which contains the classical symmetry group. And here, it's just mentioned what I already said. And there was a result by Fulton in 2006 who actually showed that the automorphism, that the trees which have classical automorphism group S2 to the K have quantum symmetry. But this is of course contained in our result as well. And only recently, there has been almost at the same time published a paper by some other person who I forgot the name, but he actually also arrived to this result that we have, and also for maybe some other classes of graphs, by using completely different methods. So doesn't use Weisfer-Lehmann or so on. So here I have again the definition of the quantum automorphism group of a graph, but I can just go quickly because here we have just what we need something more is to add some condition. So because we want to work with colored graphs, right? So we want to have some colors on the vertices and we want to preserve these colors. So we just, there is just some extra condition for that. Here is mentioned again, quantum isomorphism. Let's just go further. And so with quantum automorphism groups, something that is very easy in the classical automorphism groups has to be checked very carefully. So we have some bunch of operations that we use, and for each we have to prove that this actually preserves the quantum automorphism group. But this may be very obvious in the classical way, but still we need it. So one of the operations is, for example, that if you have just an independent set, which is a union of colors, then we can add edges between all the pairs of vertices in S. So just something like this, right? So you have two color classes and you just add all the edges between that. I mean, it's a very simple thing, but it has to be checked carefully with quantum groups. Or adding a complete bipartite graph between two disjoint sets that are also union of color classes. So something like this, you have some color classes and you add like a complete bipartite graph between these. So this also preserves quantum automorphism group. Or changing, this is like seems very trivial, that changing the color of some monochromatic vertex set to a different color, or adding an isolated vertex of a color that no longer existed. So because what we want to do, with quantum groups, we also want to use some similar kind of induction as is used for regular trees. But we need to transfer from regular trees, regular automorphism groups of trees, we need to transfer from unrooted trees to rooted trees so that we have some option for an induction. And we basically use these simple operations that we prove that preserve quantum automorphism groups to replace undirected trees with rooted trees. So how is it done? Like using this operation is very simple. So you just color the vertices, then you remove an edge, so you can also reverse the operation. Then you add a vertex of a different color. Then you add like the complete bipartite graph between two color classes, and then you uncolor. And so it seems very trivial, but somehow with quantum groups, one has to check everything carefully that it works. So it's like the process of rootification. You can just basically introduce a root to an unrooted tree. Oh, I forgot to mention that every tree has a center, which is either a vertex and edge, which is like a vertex and edge, which is like a subset of vertices that is equally distant from the leaves of the tree. And we do this process that was depicted here with the center. And that is also derootification. So really that the class of rooted trees is exactly the same as unrooted trees. So rooted trees are basically just like trees with one distinguished vertex, with one colored vertex, which has to be preserved. So here, if we have a rooted tree, what we can do is basically attach a very long path to it, and then basically we force the center to be somewhere on the path, because it will be very, very long. Longer than any path in the tree, and then we can unroot it, and basically we will get that the automorphism or quantum automorphism group is the same. So then I will maybe not define everything, just go over this. Probably you're familiar with free products of quantum groups. And then there is a free rest product of a quantum group. So it's basically this an analog of the direct product and rest product of groups. And we have two important lemmas that are also analog of what we proved for this, or what is known for these classical automorphism groups, that if we basically have a bunch of colored graphs that are all connected, we have some components, and these components are not quantum isomorphic in this case, then actually the quantum automorphism group of this disjoint union of graphs can be just expressed as a free product of these quantum automorphism groups. And similarly, if we have like a connected vertex color graph, and if we take n copies of this graph, then the quantum automorphism group of this disjoint union is expressed as a free rest product with the quantum symmetry group. And I didn't actually mention how we are actually using the Weisfer-Lehmann here, but the Weisfer-Lehmann here is used in such a way that basically Weisfer-Lehmann can distinguish all trees. So since it can distinguish all trees, then it's enough to decide isomorphism for them. So it's also enough to decide quantum automorphisms for them. So in other words, thanks to this, trees are isomorphic if and only if they are quantum isomorphic. So that's why we can apply these things for trees. And putting these things together, we get this equivalent, the quantum version characterization of the quantum automorphism groups of trees. Another result that I will mention is the Sabidusis theorem. So this theorem says about lexicographic products of graphs. So here is like some technical definition, but it's very easy. What is a lexicographic product of graphs? So basically, this is a lexicographic product of a cycle with K2, which is an edge. So basically, we take for each vertex of the outer graph, we take a copy of the inner graph. So like here we have 4 red edges and put all possible edges between the copies if there was an edge in the C4. So basically we just take a bunch of, for each vertex of the outer graph, we take a copy of the inner graph and put complete bipartite graphs between those copies if there was an edge in the outer graph X. And the Sabidusis theorem says that the automorphism group of this lexicographic product of 2 graphs is described as a breadth product of the corresponding automorphism groups if and only if some condition holds. What is the condition? So this is actually 2 conditions written in one. So if this inner graph is disconnected, then the outer graph should have no twins. Twins are vertices that see exactly the same neighborhoods. So you can imagine if this inner graph was disconnected and there were twins in the outer graph, you can think of how you could create extra automorphisms that are actually not in this rest product. So this rest product will be a subgroup always, but the equality happens if this kind of condition is satisfied for the graphs. Right, so in this case, this is like S2 rest product with D4, the dihedral group. And the quantum version is just that we replace automorphism groups with quantum automorphism groups, and we get the free rest product in there. And Chassignol proved the result by completely different methods some years ago, just for regular graphs. So just for graphs which have the same degree at every vertex. So we obtained probably a much more elementary proof for this, and we prove it for all graphs. So we make a quantum version of the Sabidusis theorem. And here we actually use the Weisfer-Lehmann algorithm more deeply. So I'm not going to now go into these counts. Let's just ignore that for now. But basically what we have to do, we have to just follow the Weisfer-Lehmann algorithm and see that the inner and outer edges. So what we want to basically prove, because what are these automorphisms in a classical case? What should they do? You should have, if this is just an equality, you should have just 2 types of automorphisms. Those that follow the structure of the outer graph, and those that act inside the inner graphs. This is just two types of automorphisms that should be there in case there is an equality. And what we use Weisfer-Lehmann to do is that we prove that the Weisfer-Lehmann actually distinguishes all the inner edges and all the outer edges. So this is just a purely combinatorial result, but thanks to the connection of Weisfer-Lehmann and the quantum groups, we can, it actually helps to also analyze the quantum groups. So it's not clear how actually Sabidusis proved it in his original paper, because this is something from the 50s, and it was there were several iterations for the papers. There were several mistakes in it. Like it was at least 3 times corrected or 2 times, and but he must have done something similar. He must somehow distinguish the inner edges and outer edges, but the Weisser-Lehmann algorithm is much more elegant way to do it, and we also not only obtained the quantum version of Sabidusi, but I think reproved the Sabidusi theorem in an elegant way. And maybe I'm coming to the end, and okay, let's just quickly go over this thing here. So we could then actually also prove this. Yeah, so we actually do the same. We could prove it by ourselves, but it's easier to use this existing result by Banica and Bichon, where they actually define yet another kind of product of graphs, which is the free. They call it free product of graphs, but. And I'm not going to define it because it's not that important now. And they prove that this quantum automorphism group of this free product of graphs is also the rest product. So, and for us to use the free product is actually exactly what we need from the Weisser-Lehmann is this partition of these inner and outer edges and non-edges. And then we can just very simplifying it now, then we can plug in to this Banica and Bichon. And this is exactly what is doing Chassignol, who proved this only for regular graphs. He's also using this result by Banica and Bichon. And yeah, and yeah, so we proved that under the Sabidusi condition, the quantum automorphism group of this lexicographic product of graphs, what we want is exactly equal to the quantum automorphism group of this free product of these graphs where they are colored based on these colors that we obtained from Weisser-Lehmann. And with these colors, because this free product of graphs by Banica and Bichon is using some colors, and we use exactly these colors from Weisser-Lehmann to plug into their product, basically. And yeah, so maybe I almost ran out of time. Here is just a very small cherry on top is that you can also you can prove a version of the Sabidusi theorem for vertex transitive graphs. This means that the graphs have just one orbit in their automorphism group. And yeah, let's just not go over this anymore, but the theorem is basically that if it's not the case that the equality occurs in the Sabidusi theorem, then for vertex transitive graphs, you can still find a formula for the automorphism group, and the quantum version happens to be exactly the same. Okay, so let's just mention some problems at the end. So something that we already have in progress is to, and there we have to do much more quantum groups, is to define inhomogeneous free rest product. So you have this rest product of groups where you have a group acting on some set. And now to each element of this set, you assign a group. Now, you can consider the orbits in this action, and for each orbit, you could pick a different group. So in this way, you get an inhomogeneous rest product of groups, which somehow generalizes the rest product. And it would be interesting to have a quantum group analog of that and see what can be done with it. So maybe apply it for some further graph classes, like planar graphs, for example. And planar graphs, there are some problems even in planar graphs that are not clear. And it might be very interesting for people working in geometry, because if you wanted to determine the automorphism groups of planar graphs, there is a key case of so-called three-connected planar graphs. If you don't want to, so three-connected planar graphs basically corresponds to the graphs of polytopes. And Mani's theorem says that they can be uniquely embedded into the sphere in such a way that the automorphisms of the three connected planar graphs exactly correspond to isometries of the sphere. So the automorphism groups of three connected planar graphs are exactly the finite subgroups of O3. And so these are some infinite families of groups and symmetric groups of Platonic solids. And so quantum Manis theorem, or yeah, and maybe because there is a quantum group O plus 3, so there might be something there. So look at maybe quantum automorphism groups of three connected planar graphs. Even that would be very interesting, I think. So that's it.
Thanks very much for that very interesting talk. Do we have any questions, either in person or perhaps online?
Yes.
Yeah, so we consider the quantum automorphism group of a complete graph. How to prevent it from
Well, quantum automorphism group of a complete graph should be the Sm plus, the quantum permutation group. Actually, I don't know much about that result. I just heard a talk which claimed this, but yeah, I think that it should be definitely true that there is no quantum analog for Crookes theorem, but I don't know exactly the statement from the top of my head. What is exactly the statement that they proved in that? Yeah. It was proven by, I think, Bishon McCarthy.
And when you mentioned the Crookes theorem and the failure in the quantum sense,
Yeah.
what I was wondering is there, so if it fails for graphs, I mean, is there some other structure for which there is a quantum version of
Yeah, I don't.
Crookes theorem, like
Sorry,
is
I
it
don't know.
some other?
I don't know, but yeah, it's an interesting question, but I don't know.
Well, classically, the point is that every group is a permutation group. So every group acts on itself. But if you have a quantum group, then a quantum group is not a classical space. And quantum permutation groups, in this sense, are symmetries of classical spaces. So if you wanted a quantum Crookes theorem, you actually should not consider classical graphs, but quantum graphs. So some graph structure on some algebras, non-commutative algebras. Okay. I have another question. So I wanted to ask again for the difference between the Weisfelder-Lehmann and the quantum isomorphism. So is the difference quantified somehow more precisely? How much is different? So in terms of computability, there's a huge difference, but how many graphs the orbits are different for Weisfelder-Lehmann or quantum automorphism? Or do we know some examples of pairs of graphs that cannot be distinguished by Weisfelder-Lehmann, but they are not quantum isomorphic or something in this sense?
Like if I understand it correctly, like if you so if they are not distinguished by two-dimensional Weisfelder-Lehmann, or because
try strongly regular graphs.
Yeah,
because Weisfelder-Lehmann says nothing about strongly regular graphs. It stops in the beginning.
Yeah, that's like yeah, maybe.
But then maybe you want the other extreme where Weisfelder-Lehmann works fine but the quantum algorithm or whatever.
Isomorphism.
Could be difficult. Like for trees, he proved that it is basically the same, but something more complicated, more complex than trees, but far from strongly regular graphs.
Yeah, right. That would also be interesting to have some large class of graphs where we know that Weisberg Lehmann would answer the question.
Well,
This in
planar
paint.
graphs, actually.
Well, planar graphs is not clear. For planar graphs, it's not clear whether two-dimensional Weisberg-Lehmann will answer the question. So planar graphs is actually the open problem whether two-dimensional Weisberg-Lehmann will distinguish them, but currently it's known that three-dimensional Weisberg-Lehmann distinguishes planar graphs, and the open question is whether also two-dimensional distinguish them. And yeah, maybe, but people believe it's going to be true.
Planar graphs, it's a choice.
Like you mean it's conjectured that
Yes, it's conjectured.
that it works even for the classical automorphisms.
Yes.
Yeah, right. So
But for classical, it is not clear whether dimension 2 or dimension 3 is fine. About quantum, who knows?
Yeah.
It could.
yeah, well,
Right.
if the classical the conjecture was true, then it's not that interesting for the quantum case. But if it was not true, then maybe it is.
Yeah.
Outer planar graphs.
Yeah. That's a good question. Not.
Right. Any other? Please.
Maybe difficult question.
So can you explain where this undecidability comes from? Why it is not decidable? Because in the classical case, you just check all the bijections. But why here there is problem that there is no algorithm?
Yeah, I don't know the
I
problem.
don't know.
I just don't know.
Maybe
It's
difficult
undecidable.
there. But you must check, I mean, it should be the problem that you have to check infinitely many possibilities. Otherwise,
yeah, definitely.
stupid algorithms would exist.
Yep.
All right. So if there's nothing further, then maybe let's thank our speaker again. And next week we will have somebody. Then I hope you will join us. Okay.